Hi everyone, my name is Vikas Nandwana. I'm a research associate at the Department of Material Science at Northwestern University. So today I'm going to talk about a novel oil spill remediation platform, and we name it OHM Sponge. So I come from Professor Vinayak Dravid's group. So one of the main focus in our research group is the environmental remediation, where we use nanoscale approaches to solve Gigo-ton problems. And you will see in this conference various presentations from the group. Today I will be focusing on the oil remediation, and then we have other members who are presenting on the nutrients and heavy metals also. So when you think about oil spill, the first name that comes to our name is, come to my mind is Deepwater Horizon. But the fact is, oil spills happen every day in some part of the world. Last year in US alone, more than 20,000 oil spills were reported, ranging from tens of gallons to hundreds of thousands of gallons. And this oil spill affects human health, such as skin, respiratory issue, marine life, aquatic ecosystems, plants, animals, and also fishing, tourism industry. And that's because of that, and that generates a lot of issues actually. And there are several methods which are present, which are already present for to remove the oil. The first one is the dispersant, where the oil is dispersed using the chemicals. The second one is the burning, where the oil is just simply burned. The third one is the skimmers, where oil is pumped using these pumps and the booms. And also the fourth one is the sorbent, where oil is just selectively absorbed. Each of this method solutions have their advantages as well as disadvantages. Like dispersants and burning are a fast method, but burning is very harmful for environment since it generates carbon emission, and dispersants are toxic for marine life. Similarly, skimmers are slow and inefficient in some conditions, and sorbents are one-time use, so very expensive and generates a lot of physical waste. So there's not a single method which is cost-effective or fast or selective, and in a way it's economic or efficient and also eco-friendly. And that's where our technology comes in. By coating commercially available sponge using a multifunction nanostructures, we have developed OHM Sponge, which is oleophilic. That means it loves oil, and hydrophobic, which means it resists water. So when you introduce this in an oil-water mixture or oil-water interface, it selectively absorbs oil and just repels water. As you can see in the below figure, that water droplets do not enter the sponge, they just make a balls here, and if you see the next, there is oil which is completely absorbed in the sponge. So because of this, when you introduce this OHM sponge to any oil spill, it selectively absorbs oil, and then just this oil can be again recovered by squeezing it, and then the sponge can be reused many number of times. The reason why we call it economic is because it's made of a cost-effective materials. It's made of just iron and carbon kind of coating, and then it's also reusable. So it kind of can be used multiple times, so that reduces the cost effect drastically. It's very efficiently because it's very selective. It selectively removes the oil, and then it can recover the oil also. And finally, it's very eco-friendly because it does not affect any marine life. It does not generate any carbon emission, and also it's made from environmentally friendly methods as well as materials. So the way we make the sponge is we just take any base sponge. The sponge could be polyurethane, cellulose, melamine, or any other porous material, and then we dip coat in this nanocomposite slurry, which is made of a graphitic carbon and iron based nanostructures. And that's how the OHM sponge is formed. So on a simple strand of a basic base polyurethane sponge, there is a very thin coating of a nanocomposite which looks like this. This is the transmission electron microscope TEM graph, and you can see the composite has a layered structure of graphitic carbon as well as the magnetic nanostructures, and that coating basically makes it more functional, the sponge. So here on the right side you see the characterization plot. Figure A and B are the scanning electron microscope image, where figure A is basically just a blank polyurethane sponge, and figure B is the coated sponge, where you can see a very thin coating of a nanocomposite. And then figure C and D are the cross-section transmission electron microscopic image, where the coating can be seen. The approximate thickness of this coating is around 1 micron, less than a micron, and that is because of just this thin coating. It changes the overall function of the sponge. Figure E is the electron diffraction pattern, and figure F is the X-ray diffraction that confirms the presence of this iron oxide and the carbon in this composite. So that is how it works. Unfortunately, I could not show the video, but here what you see is that there is a oil, red dyed oil. When you put that in on a oil on a water surface, it makes like this kind of a circle, and then when you add OHM sponge to it, it selectively absorbs this oil, and then just you can then squeeze it out and reuse a multi number of times. Not only that, it can remove the oil also below the surface of the water. So here is the chloroform, which is heavier than water, so it settles down. And when you introduce the OHM sponge, it can selectively absorb. It does not absorb any water. It just take the chloroform and take it away. We have done many tests using this OHM sponge for selectivity as well as the reusability. So as you can see that this the y plot is, and the y-axis is mass absorption capacity, which is nothing but ratio of the mass of absorbed oil divided by mass of the sponge. So you can see, depending on the different kind of oil, the OHM sponge can absorb almost 30 times of its weight. And we have used all sort of synthetic and processed oil from hexane to pump oil, and we have seen it goes from 20 to 30 times of its capacity. The bottom plot is the reusability plot, where we have squeezed it and reused it again. And what we have seen is, even dozens of times, it doesn't change any capacity. Here we have shown for 10 times. You can see the absorption capacity does not change, almost stays close to 30. Similarly, when we tested this sponge for a different aquatic condition, like different pH or different salinity. For pH, we have tested water with 1 to 13, and you can see that absorption capacity does not change dramatically, as well as for salinity from 0 to 1. While the ocean salinity is 0.6 molar, we have tested up to 1, and we have seen there is no significant change in the capacity and mass absorption capacity there also. So it does not get affected by either pH or salinity, and it works on mostly all sort of oils. After this, we have tested crude oil. So we have acquired some crude oil from some of our collaborators of Chevron, and we tested 5 crude oils with different viscosity, which differs in viscosity as well as density. And what we see here is it works on all sort of crude oil, whether it's a West Texas, which is the very less viscous, to Azerbaijan heavy, which is very highly viscous oil. It works on all oil. The number depends, the capacity changes because the change in the viscosity of the oil. The method is very economic and also scalable, because we can produce this nanocomposite slurry in a flow reactor in a very with the high flow rate. So what you are seeing here is the production which we have done for 4.5 liter in 30 minutes. So we can generate almost 9 liter per hour, the slurry of this material. And that to just give a context, that can coat around 40 OHM sponge sheet, which is 1 foot by 1 foot by half-inch thickness. And basically, those sheets are enough to absorb almost 500 liter of oil. So that gives you some context that this method is very scalable. And here on the right side, you can see we have coated all different size of sponges, and the thickness of the sponge, what we have coated is 0.5. But size and shape does not matter, since it just depends on the dip coating. We can use any sponge of any size and shape. To get this external validation, we have recently visited OHMSETT Facility, which is the largest oil spill response testing facility in North America. And we tested the sheet of 50 sheets of this 1 foot by 1 foot of by 0.5 inch of OHM sponge under various conditions, where oil of different viscosity was tested, stationary and moving water, and to test the oil sheen. And OHM sponge result were obtained at OHMSETT were similar or even better than the laboratory conditions. So this is the largest water tank to generate a real world applications for the OHM sponge. And we are quite happy that we kind of passed their test also. So this is just some media coverage in the last few months. OHM sponge have received, especially we were very fortunate to get featured by the National Science Foundation, and they created a video also, and I can share the link with everyone about that video, as well as the Science Daily, CNDN, on other international media also covered, from Forbes to Wall Street Journal and Guardian.
About 3 minutes left.
Sorry, how much?
About 3 minutes left.
Okay, that's good. So now what I would like to say is, not only it's a solution, we are developing this as a platform, actually, OHM sponge. So the idea is, it just is not limited to oil. Basically, we can coat any sponge with, if we modulate the coating on the sponge, we can selectively absorb other pollutants which are present in water, soil, and air. So then these pollutants can be recovered, and then the sponge can be reused. So it could work for any kind of pollutant, as long as we have a coating available for that pollutant. And that is what we have been doing in our lab. We have been developing different kind of coatings to selectively remove different pollutants. And that is why it is developing as a platform in our lab. And for now, just like I gave an example of majority of oil. So we are developing another solution for minority of oil, while oil is only in the minority like ppm level, and we are able to remove that also from, for example, like a fracking water. So we are able to remove that kind of 1000 ppm of oil to less than 50 ppm oil. Similarly, we have other students who will be talking about nutrients and heavy metal toxin, and also there is work going on microplastic. So with this, I would like to conclude my talk. I would like to thank Professor Dravid and Dr. Roberto Dos Reyes, Stephanie, Ban, Yash, and other group members. They have been tremendously helpful in the group's research, as well as the funding agency, NSF, and Nuance Shine. And finally, I would like to just share this news, where OHM sponge was featured by National Science Foundation homepage, actually front page, on June 5th, and that gave us a pretty good visibility. So with this, I would conclude my talk and would be happy to answer any questions. Thank you very much.
Great, thank you so much. It's so interesting. Are there yep, already I see questions coming in.
How are the sponges cleaned so that they can be reused?
Oh, that's a very interesting. So basically, all we need to do is, you can take any kind of a wringer, and all we need to do is we need to just squeeze the sponge under the wringer, and most of the oil, 90 to 95% oil, gets recovered. And of course, there is some sort of a maybe 1 to 5% oil stays back. It's just similar as a kitchen sponge. You know, when we have a kitchen sponge, it soaks with water. We can recover most of the water, and there is always some water which stays back in the sponge. It's very same thing.
We had another question about the makeup of the sponge. You state the sponges are made from benign materials, yet oh, it moved, I'm sorry. Yet the headlines you presented state that it's polyurethane.
Oh, so basically polyurethane is, as I mentioned, polyurethane is something which we just started with. And of course, yeah, it's a polymer, but as I talked about that, we have things going in the pipeline which are based on other recyclable material like cellulose. Cellulose is something biodegradable, and we have been working on the similar formulation on cellulose also. And so that is the reason I mentioned that we can definitely go with, we can replace the basic substrate. Actually, the sponge does not depend on the basic substrate. It could be anything, and ultimately we plan to replace all the substrate with the biodegradable substrates.
Great. And I think we can take this last question, Janice.
Excellent. It's about when you're cleaning the sponges, when you squeeze and reuse your sponges, are they just squeezed by your hands, or is squeezing force carefully controlled by some other instrument?
Yeah, we use it a wringer. Actually, if you squeeze it by hands, it's not never uniform actually. And ideally, we have a ringer in our lab. Just you can think about, in old times there used to be washing, the washing ringers where they used to wash the clothes in that. It's the same mechanism. There are two rollers. The sponge is rolled under those two rollers, and most of the oil is recovered by that.